Unit 2, Elements and Molecules, Lecture 4. Let's name ternary salts. But first, how do we recognize ternary salts? Well, now that you're familiar with the table of oxidation numbers, you're going to find it's kind of simple, because ternary salts consist usually of a metal and a polyatomic ion, or a radical. And we've looked at an awful lot of those radicals. Here's an example: calcium with a sulfate radical. Now the way you go about naming them is this. You name the metal, and if the metal happens to be a multivalent metal, then use an appropriate ending to indicate which oxidation state it is, or use Roman numerals, but only do that if it's a multivalent metal. Then you name the polyatomic ion or the radical. Let's look at some. Consider these. Let's start here. How would you name it? Well, the polyatomic ion is sulfate, and the metal is zinc, and it's not multivalent, so it's very simple. Zinc sulfate. How about this one? Well, the polyatomic ion is, that's right, it's sulfite. And the metal, and again, this is a monovalent metal. It only has one oxidation state. So the answer is sodium sulfite. Notice, we didn't have to indicate how many sodiums we have because you're born knowing that if sulfite is -2 and sodium is +1, you've got to have 2 sodiums to go with it. And what about this? Well, the radical or polyatomic ion is carbonate, and the carbonate is what kind of a charge? That's right, it's a -2. So the iron must be a +2. Therefore, the name of the compound is ferrous carbonate or iron 2 carbonate. Now, folks, look, logically, the iron 2 carbonate is an easier way to name these. But quite frankly, the ferrous term is one that's very old and is thoroughly steeped in chemistry. And you will find very often, particularly when you go into the lab, you may find instead of seeing iron 2 carbonate, you may see it as ferrous carbonate. So it behooves you to understand both ways to name these. So get busy with those flashcards. Now how about this? Well, we have nitrate, which is a -1. And there are 3 of them, giving us a total of -3. So the cobalt has to be a +3. Now, is it multivalent? Yes, it is. So the cobalt then must be a +3 as opposed to another charge, and the other charge is a +2. Therefore, this is cobaltic nitrate or cobalt 3 nitrate. I'm confident that you have the idea now. You might want to stop the video and try your hand at naming these. And then when you're ready to see their names, start the video back up and I will show you what I got. Looking at this first one, I see that this is sodium hypochlorite. Sodium hypochlorite. This next one has a polyatomic ion, the sulfite, which is -2. There's one of them. So the mercury over here must be a +2. And there are 2 of those, so each of those mercuries must be a +1. Therefore, this is the mercurous sulfite, or if you will, the mercury 1 sulfite. This next one with the carbonate radical is -2 radical. There's 1 of them. So the nickel must be a 2 positive, and there's only 1 of them, so it's a 2 positive. And if you recall from your polyatomic ions, that is the nickel-us radical. I'm sorry, the nickel-us ion. So that is nickel-us carbonate, or you can call it nickel 2 carbonate. This next one is the oxalate radical. The oxalate radical is a 2 minus, but there are two of them, which gives us a 4 minus. The 10 then must be a 4 plus, and there's only one, so it by itself must be a 4 plus. This is the stannic oxalate, or the 10 4 oxalate. Down here we have a phosphate polyatomic ion, and we have barium, and barium is not multivalent. So this is very simply barium phosphate. Quaternary nomenclature, 4 different elements. Now, there are really two different kinds we're going to deal with. We're going to deal with what we shall call acid salts for use as a descriptive term. And we'll also deal with mixed compounds. Let's start with the acid salts. Now, just what do I mean by an acid salt? It's a salt that contains one or more hydrogens that have been left over from a neutralization process of the acid. That's one way of thinking about it. For example, NaHSO4. Now imagine that you had sodium hydroxide and sulfuric acid in a neutralization reaction, but there was not enough sodium hydroxide to completely neutralize the sulfuric acid. Maybe there was only about half enough. So it only neutralized about half of the hydrogens. So you wound up then with a salt with a residue of the acid hanging in there, plus water, NaHSO4. Now what we need to look at is how to name it. Well, there are two names for it. One is very straightforward and very logical. Sodium hydrogen sulfate. Sodium is a +1. Hydrogen's a +1, sulfate is a -2, the whole thing is electrically neutral. But there is a common name that is used for it, and that is sodium bisulfate. The old way of naming it is to refer to hydrogen in the middle of the compound like this as sodium bisulfate. Now on basis of that, why don't you try this one? Did you get potassium hydrogen carbonate or potassium bicarbonate? Now, this way of naming things generally occurs with the -2 radicals, the -2 polyatomic ions, particularly with sulfate and carbonate, and there are some others. When we look at the table of common oxidation numbers, you will find these down here in the -1 column. Because we took the -2 radical, we added a hydrogen to it which has a positive charge, and so that caused the charge of the new radical to be a -1. And these are the common ones: bisulfate, bisulfite, bisulfide, bicarbonate, and binoxalate. And notice that for binoxalate we put an N after the bi to ease the pronunciation. Now, what about salts from triprotic acid? We just looked at salts from diprotic acids, but what about the ones from triprotic acids? Well, there are two different acid salts that can easily be formed. Consider, for example, the acid phosphoric acid. Now, suppose you don't replace all the hydrogens. Think about treating it with sodium hydroxide. But don't replace all the hydrogens. Maybe replace two of the hydrogens. Or maybe replace one of the hydrogens. Then do you see you could get two different salts, like this. There's an Na2HPO4 and an NaH2PO4. The term bi cannot be used here. It's inadequate because it doesn't distinguish between the two, and you don't want to say bi and dibi. That gets too confusing. So let's see how they're named. Here we go. Let's consider Na2HPO4. Remember, that's one of the salts from phosphoric acid. We can call it sodium monohydrogen phosphate. And of course, if you're saying that there's only one hydrogen, and then sodium is a +1, do you see there must be two sodiums there to make this compound be electrically neutral? Well, here's another way, and this is almost overkill, but it's disodium monohydrogen phosphate. That eliminates any confusion, doesn't it? It's very, very straightforward. But quite frankly, in the lab, you are probably going to see sodium phosphate dibasic. Now let's see one way of looking at how that might happen. If there is insufficient sodium hydroxide to react with phosphoric acid, then you could have the reaction like this. 2 sodium hydroxides plus phosphoric acid to give you the Na2HPO4. Thus, as we look at it, we see that 2 of the hydrogen acids have been replaced. Therefore, we say, oh, it's reacted with 2 base units. Therefore, it's sodium phosphate dibasic. That's not really the reason we do it, but we're not into hydrolysis yet. So this is a way that you can look at it. Let's look at the other one now. Consider the NaH2PO4. And again, if insufficient sodium hydroxide reacted with it, maybe this time 1 sodium hydroxide reacted with the phosphoric acid and took out one of the hydrogens. Thus, 1 acid hydrogen has been replaced. Then that one we would call sodium phosphate monobasic. And let me remind you, this is just a way of looking at it. This name is a very real name, and why it comes up with that actually has to do with hydrolysis. But that is a subject that we'll get to significantly later in the course. If you got a way to look at it, go back and review it and find a way to remember it. Let's look at these salts. We're still going to deal with boric acid. That at least eliminates one problem. Let's look at this one. Now, what are you going to name it? Name it the way you might see it in the lab. Potassium borate dibasic. Did you get that? How about potassium monohydrogen borate? Yeah, that will work, but it's not likely what you're going to see in the lab. Or what about dipotassium monohydrogen borate? That's that overkill one, huh? Well, what about naming this one? How would you name it? Potassium borate monobasic. Or, if you will, potassium dihydrogen borate. Or monopotassium dihydrogen borate. I think you're going to find that that potassium borate monobasic is the more common one that you will see. So remember the rule. We indicate the number of hydrogens lost using the term monobasic for 1 missing hydrogen or dibasic for 2 missing hydrogens. Now, using that principle, can you see another name for this? Do you see why it may often be called sodium borate tribasic? That's right, it's missing all 3 hydrogens. Mixed compounds are, for the most part, pretty straightforward. For example, look at this one. It's a compound of sodium, potassium, with a sulfate polyatomic ion. And what do we call it? Sodium, potassium, sulfate. You do have to keep track of charges, however. Look at this one. Potassium, aluminum, sulfate. Potassium is +1, aluminum is +3, therefore you have to have two sulfates. Potassium, aluminum, sulfate. There are some other compounds that look like mixed compounds, but they really aren't. They go in another classification, and we'll deal with those when we get there. You're not. Some other names we need to look at are hydrates, some special cases, and common names. Let's start with hydrates. Hydrates are compounds that contain a specific quantity of water. For example, here's one in which we have the compound cupric sulfate, and it is bonded to 5 molecules of water. So it has 5 molecules of water for every single formulation of copper sulfate. How do you name it? You name the compound, and then you indicate the number of water molecules by using those prefixes we've talked about. So this compound then is called, this one right here is called cupric sulfate pentahydrate, or of course it could be called copper 2 sulfate pentahydrate. And notice the comma that separates the name from the number of water molecules. Remember the punctuation. Here's an example. See if you can name it. And what did you get? Did you get oxalic acid dihydrate? It's really pretty straightforward. Some special cases. This is one in particular, and students really find that ammonia can be confusing. And I think it's because sometimes people use the term a little loosely. For example, now, ammonia is a gas. Ammonia is a gas. However, it is extremely soluble in water. And when dissolved in water, it may be represented as ammonium hydroxide, or it may be represented as ammonia in water, which is very often called aqueous ammonia. So we have ammonium hydroxide and aqueous ammonia. Now I want you to look at the formula. The NH4OH is the same thing as NH5O. The ammonia in water is the same thing as NH5O if you were just to add the numbers of those atoms together. So they're really interchangeable topics. But when you talk about ammonia, ammonia is a gas. But these others are a gas dissolved in water, and they make solutions. And the solutions are characterized as ammonium hydroxide, or you may call it aqueous ammonia. They are, for all practical purposes, as far as we're concerned, the same. There's another common case, and that's the cyanide ion. Well, it doesn't really give us a lot of trouble, except naming its compounds doesn't quite go along with our rules. For example, NaCN. Now that's a ternary compound. It's sodium, carbon, and nitrogen. But it's named as if it were binary, and it is called sodium cyanide. So don't let that situation bother you too much. That's going to happen sometimes. When we're naming things, we very often introduce historical terms and historical names, and those names have carried through with us. And sometimes it's not going to fit our attempts to be very organized with nomenclature. Well, let's give you an opportunity to see how much of this you remember. We'll let you try your hand at giving the formulas for several compounds. In our first one, chromic acid, we have a perfect example of the way in which the name can tell you how the formula is done. For example, this does not have the prefix hydro. And since it doesn't have the prefix hydro, this must be a ternary acid. And as a ternary acid, do you recall that the name depends on the name ending given to the polyatomic ion? This is chromic acid, so that must have come from the chromate radical. Well, the chromate radical is CrO4 with a -2 charge. Therefore, it's going to have how many hydrogens? That's right, it's got to have 2. So it's H2CrO4, chromic acid. Now let's look at this one. Arsenic sulfate. Well, arsenic gives us a clue that it is a multivalent element. And it is. It has a +5 charge and a +3 charge. The +5 charge is the arsenic. So this is going to be 5+. And sulfate, if you remember, is the polyatomic ion with a -2 charge. The least common multiple of the two is 10. So I'm going to have 2 of these right here, and I'm going to have 5 of these to get my oxidation states to add out, to be electrically neutral. So it's going to be arsenic, As2, and sulfate is going to have to be in parentheses, SO4, close parentheses, 5. Arsenic sulfate. Now let's look at this next one, ammonium hydroxide. This is a radical NH4. And do you recall that NH4 is a +1 charge? And hydroxide is another polyatomic ion, and it's a -1. Oh, it's very simple then. NH4OH. Diphosphorus pentoxide. Look at these prefixes. Di here and pent here tells us it's 2 nonmetals. It is P2O5. Now let's look at this last one, lithium arsenite dibasic. We often save the best for last. Lithium arsenite. That must be a salt that is coming from an acid, a triprotic acid, arsenous acid. Almost misspoke myself there. Arsenous acid. Now it's dibasic. And being dibasic, it tells us that 2 of these hydrogens right here have been replaced. Well, lithium is a 1+. It's replacing 2 hydrogens, so the formula is Li2HASO3. Lithium arsenite dibasic. Common names. These are things you really should know. NaOH, sodium hydroxide, to the layman is called Li. NaHCO3, to the chemist is sodium bicarbonate, but to the layman it is baking soda. Oh no, by the way, its old name was bicarbonate of soda. This, to the chemist, is acetic acid. But in a 5% solution to the layman, it is called vinegar. H2SO4, to the chemist, that is sulfuric acid. The layman knows it as battery acid, and battery acid has a very specific concentration when used in the lead storage battery, but that's for later. HCl, or HCl aqueous, to the chemist is called hydrochloric acid. But to the layman, it is muriatic acid. Muriatic acid. Sometimes it may be called crete clean because it's used to dissolve concrete or to groove concrete or to remove little nubby things on concrete. CaO, to the chemist, is calcium oxide. To the layman, it is lime. Take the lime and put it in water. To the chemist, it is calcium hydroxide. To the layman, it is slaked lime. That's right, it's calcium oxide in water. It's a way of sweetening soil, for example. CaCO3 to the chemist is calcium carbonate, but the layman knows it as limestone, marble, chalk, or shells. To the chemist, it is potassium carbonate. To the layman, it is called potash. And sometimes there will be, for the terms that sometimes there will be some potassium hydroxide mixed in it. To the chemist, it is dinitrogen monoxide. To the layman, it is nitrous oxide. Well, we have covered a lot of things. After a brief introduction, we talked about a little bit of the history of atomic theory and how the concepts came to be. We talked about atoms and isotopes, and particularly mentioned the mass spectrometer, or the mass spec. We did a brief study of the periodic table just to make sure we're on the same wavelength there, and we did a pretty detailed section on nomenclature. Ah, yes. A better way to teach and learn chemistry.